Welcome to another curve sketching example. So in this example, we have the graph of f prime. And our job is to sketch a possible graph of f given this graph of f prime. So again, we're going to do our number line based off of f prime. We'll do a number line based off the second derivative, and then do our graph. So for our number line for f prime, for our number line with f prime, again, we're looking for, we want to know the critical values of f. We want to know where is f prime equal to 0 or undefined. So based off this graph, again, this is the graph of f prime here. This graph doesn't look to be undefined anywhere, at least not where we can see. So we're never undefined. But we can see that it's equal to 0. Again, this is the graph of f prime. F prime equals 0 when we cross the x-axis. Okay. So this occurs when x equals -3 and +2. Then we'll need to figure out where our derivative is positive and where it's negative. Again, this is the graph of f prime. So for this whole stretch, until we hit the x-axis, that's f prime is below 0. F prime is negative. And then the next stretch, all of this is above the x-axis, so we have f prime is positive or greater than 0. And then our last stretch, again, that the y values are positive, the y values are f prime, so we have f prime is greater than 0. So if we do our number line between -3 and 2 are our points of interest, that's x. F prime, we are 0 at those 2 points. F prime started off negative, switched to positive, hit the x-axis, and then went back positive again. Right. So again, here we're not looking for where this graph is going up or down. We're solely looking for where is it above the x-axis, where is it below. So essentially what we are doing is anything up here is f prime greater than 0. Anything down here is f prime less than 0. F prime is our y value in this graph. So we know for our function f that we start off decreasing, flatten out, and we go increasing, flatten out, and then we increase some more. So we know that f has a relative min at x equals -3 and a relative max at x equals 2. Sorry, not a relative max, no relative extrema at x equals 2. It goes up, flattens out, and keeps going up. So no relative extrema at x equals 2. It just flattens out for a moment. So we can again do our second derivative. So we can find the number line for the second derivative. So I'm going to go ahead and just once again copy in what our graph looks like. So let me just quickly do that. All right, and then let's go ahead and erase all my comments here. So again, this is the graph of f prime. So the second derivative is the derivative of f prime. Right? So we're looking at the derivative of this graph. So second derivative equals the derivative of this graph. So if we want to know where the second derivative is 0, we are looking for where this graph has sloped 0. So if we're looking for where this graph has sloped 0, that's where it turns around here and here, right? So we have slope 0 somewhere around x equals negative 1.5 and at x equals 2, right? So these are our points of interest. If we want to look where it's undefined, it's never in this case. So our only places of interest are at negative 1.5 and 2. Then we have the second derivative is positive, means that the f prime is increasing. So if we look for where f prime is increasing, we're looking for where the function is going up. So it's increasing before negative 1.5, and then it's increasing again after x equals 2. Right? And then it's decreasing. The second derivative is less than 0. This happens when f prime is decreasing. So if we look for that, that happens between negative 1.5 and 2. So if we drew our number line, we had points of interest at negative 1.5 and 2. The second derivative was equal to 0 at both of those points. We figured out that it's positive before negative 1.5 and after 2, and it was negative between, right? So again, in terms of my color coding, right, where f prime is going up, the second derivative is positive. Where f prime is going down, the second derivative is negative. So now if we look at what this means for f, positive second derivative, we're happy. Negative second derivative, we're sad. Positive second derivative, we're happy. We're changing concavity, passing smoothly through. These are both points of inflection. So we know that f has points of inflection. x equals negative 1.5 and 2. It's concave up for negative infinity to negative 1.5 and 2 to infinity. And it's concave down between negative 1.5 and 2. So putting this all together, some students like to put this all on one number line with just lots of stacking. So if we did this all in one number line with lots of stacking, our original points of interest were at -3 and 2. So we had a point of interest at -3. At 2, we had another point of interest at negative 1.5. Then we had x, f prime, the second derivative, and f. Let's actually do these in 3 different colors. So the first derivative was 0 at -3 and 2. The first derivative was negative, then positive, then negative. Then the second derivative started off positive, passed through 0 at negative 1.5. Switched to negative, passed through 0 at 2, and switched back to positive. And then the function f, we know that we're increasing and concave up. So we start off increasing and concave up. Sorry, wrong one. We are negative. So we'll start off decreasing, flatten out, increase. That works well for concave up. We have a point of inflection at negative 1.5. We're going to switch to concave down here. We had a min here. Our function is still increasing at this point. We're going to switch to concave up at the end, and we're still increasing. We'll have a point of inflection here instead of a max or a min. If we look at our graph, we don't know what the y values are, so that's less important to us. The main thing is that we know we start off decreasing, have a minimum at x equals -3. So let's go ahead and put our minimum somewhere here, down below the x-axis. Then at -1.5, we're going to have a point of inflection, and we'll have another point of inflection at 2. So we're going to start off with our relative min at -3. Then at -1.5, we're going to switch. So we had our point of inflection. We're still increasing. Then we're going to flatten out at x equals 2. And then we're going to turn to concave up and keep going up. So our function here, we just have that one relative minimum, no relative maximum. And our points of inflection are just where our concavity is changing. The key thing at x equals 2, the function does flatten out and change concavity. So these are both points of inflection. And then we have a relative min at x equals -3. There is no way for us to tell what the y value is because we have no information about the original y values. But this is just a rough sketch. Again, I do recommend doing 2 separate number lines. Maybe draw both number lines sort of right next to each other so you can see how things line up. As you saw when I was doing this, it's really easy to forget which positive sign and negative sign is corresponding to what. And so it's easy to then mix up where we're increasing and decreasing. So while you can put it all on top of each other like I just did here, I do recommend breaking it down, having your 2 separate number lines, and then maybe just lining the 2 number lines up on top of each other to see kind of how they interact with each other. But this is a rough sketch of our function f. Again, you may have one that's higher or lower. The x-intercepts will be at different places, but this should be kind of the basic shape of your graph.